Hello everyone, welcome back to my channel math_exc, and today this is a bonus video, so this is just like a bonus video. You can just watch it out for fun. And what I'm going to talk about is a proof of infinitely many prime numbers right here. So this proof is made by Euclid many years ago. So yeah. And first of all, this proof contains like a strategy of proof. Like this is a strategy by proof by contradiction. So basically you need to like assume the opposite of our statement right here, and then you can like just derive it truly and to see that it contradicts this, so therefore the original statement must be true. And that's what are we going to do today. So we're going to assume the opposite of our statement. Assume there are a opposite of infinitely is this finite many finite actually there are a number of finite prime numbers so we'll just name these prime numbers as P1, P4 prime, P1, P2, and all the way to P of n right here. So as you notice, this is a finite number of prime numbers, so there are n many prime numbers right here. So we're going to introduce another number. Let's say the number is capital A, and this is, we're going to derive it as the product of all the prime numbers, so P1 times P2 times all the way to Pn, and then we're going to add plus 1. Now what's important about this plus 1 right here is we're going to prove it, we're going to see later. And right here, if you can notice already, is that A is always greater than the biggest prime number, and I should have said this is Pn is the biggest prime number. So notice we took the product of all this, and this is obviously bigger than Pn itself, and then we add a plus 1 right here. And what that tells us is that A must be composite. And composite is mean not prime, so it must have at least one factor that it isn't 1 or itself. So yeah. And you can just simply see that because if A was a prime, that we just contradicted that Pn is the biggest prime. So yeah. So I'm going to write what we have said. So we define A as P, the product of all the primes plus 1, and we have A is composite here. And what that tells us is, if A is composite, there must be at least one prime that perfectly divides A, or you can say A is divisible by one of these, at least one of these primes, and we don't know how many primes that A is divisible with. So we'll just write this as follows. So P of, let's say P of small a is this bar right here, and we read this notation as P of A divides A, or A is divisible by PA, where the A is between the interval 1 and n, and this is because if you have like way beyond n, so this isn't a prime number anymore, so yeah, this has to satisfy this. And we can assume, without loss of generality, we can assume that P1, we'll just assume that P1 divides A, so it doesn't divide the whole purpose at all. So we're going to set up an equation regarding A and the divisibility of P1 right here. So we have A of P1. Notice this is an integer because we just said that the P1 divides A. And note we derive A as this, as follows before. So we have P1 times P2 times all the way to P times n, and all of them plus 1. And this is all over P plus 1. I'll just rewrite the next it again. And what I'm going to do this step is I'm going to separate the fractions into two parts right here. So this is P1. So I'll just rewrite this, and you'll see why later. So the product of all the primes over the first prime P1, and this is plus 1 over P1. And you can notice that this and this cancels very nicely, so we have A over P1 equals P2 times P3, the product of all primes except P1 because we just cancel that out, plus 1 over P1. And notice we have something interesting right here. We just assume that P1 is divisible by A, and therefore this must be an integer. I'll just write Z as an integer, and of course this whole thing is also an integer because P is a prime is also an integer, so you can just take the product of all that and still be an integer. However, this thing right here is not an integer. So this is not an integer, and you may ask why, because P1 is greater than 1, and you can clearly see we have assumed P1 is 1, therefore P1 is not at all a prime, because 1 is not a prime at all, and it cannot be less than 0 or less than 1 because it will be not a prime anymore. We define the prime as like something like a factor, something that has a factor with only 1 and itself. So yeah, that defeats the whole purpose of this. So we have clarified that we have a case where Z equals Z plus not Z. I'll just write this as like Z and across. So we have integer plus not an integer, and therefore this is a contradiction. And therefore our original statement where we have finitely prime numbers is wrong. And therefore we have supported the claim. I'll just rewrite here. There must be infinitely many prime numbers. And what that makes this proof interesting for me is that because we have the proof by contradiction right here, and this is very interesting at the start because we have choose a special number to add on here. We have plus 1, but instead we have if you have plus 2, then plus 2 is a 2 is a prime. So if we have assumed that P1 is 2 plus 2, and then this will be just a correct one, conditional correct statement. So we weren't able to prove that without the plus 1. So this plus 1 is very special. And what another thing that makes this interesting is that this uses like many like understanding about math skills. Like, so if we assume that the product of this is bigger than that, and this is the biggest prime number, then therefore this is bigger than this, and then there's A must be composite. And yeah, there's all this stuff, and we have arrived at the conclusion with this thing right here. And yeah, there we go. So hopefully you guys enjoy this video, and subscribe for more of these videos. I'll try to upload every day, possibly every day, and I'll see you guys